Um, shall we take one question now and then move on? How about that?
Sure, yeah. Are the
One
ones
question.
are the ones in the room, or should I go to the ones on Slack?
Actually, why don't you just maybe if you have anything to add on I haven't looked at the Slack. If you have anything to add, you can, and then you can just move on.
Okay.
However
All
you
right. All right. Let's do that. So there was a question. Sorry, I'm looking this way because I've got Slack open here. About the question is, why does F of R gravity not have a cosmological constant, but our scalar tensor theory does? So actually, the way I wrote them down is I took out the cosmological constant as soon as we went to these theories. So here was scalar tensor gravity. I haven't explicitly written a cosmological constant in here, but of course, when you choose this potential U of phi, you could add a constant to it. And really what you would like to happen is you would like not to have to add a constant, right? You would like your scalar field to do the accelerating of the universe and kind of take over from dark energy without having to add a constant. But it's actually quite hard to make a theory do that. So sometimes people will explicitly add a constant there, sometimes not. And for F of R gravity, a sort of similar story. It doesn't natively look like it has a constant, but in your choice of this functional form of F of R, you can pick something that either has a constant or reduces to a constant in a particular limit, which is the case with all of the potentials that happened here. Okay, so I think that answers that one. Someone else has asked about non-local theories of F of R gravity. Those do exist. I will post some links to some papers and things on those after the lectures. Okay, so let's get back on track, and hopefully that goes into presentation mode. So I'll start a timer again. Okay, doke. So we went through variational procedures, we went through scalar tensor gravity, and we looked at F of R gravity and saw it was really a sort of scalar tensor theory in disguise. Time to meet a very different gravity theory. This is, I think, perhaps one of the most mathematically sticky bits of the lectures. So hang in there. If you can get through this, you can get through the rest of the lectures, no problem. The reason I want to push through some of the maths is because it has a very interesting prediction that made it a very important theory. And that is DGP gravity. So DGP stands for Diwali, Gabadadze, and Porati. Those are the surnames of the authors who originally invented this theory around about the turn of the millennium. DGP gravity is a brane world model. So it conceptually says that there are extra dimensions to the universe. That's how it breaks Lovelock's theorem. And specifically, it's a 5-dimensional theory. So it says that there's this 5-dimensional bulk space-time, and gravity fills all 5 dimensions, whilst matter and our universe is confined to a 4-dimensional brane in that 5-dimensional space-time. And you can have great fun trying to get ChatGPT to draw you illustrations of that, as I did here. Don't ask me what the big spherical blobs are. I couldn't get ChatGPT to remove them, but we're living on this brane in this bulk. So let us write down an action for this theory. Okay, here we go. It's getting a little bit more complicated. So this action has several pieces. So there's several integrals going on here. Our first integral is now an integral over 5 dimensions of space-time, which we'll label with a coordinate capital X. And you can see its contents kind of look like the Einstein-Hilbert action, right? It's still got that root minus g, it's still got the Ricci scalar, but this time the Ricci scalar is the Ricci scalar of our 5-dimensional metric. And this piece of the action is multiplied by some mass scale, kind of like the Planck's mass, but now it's the kind of mass scale of this 5-dimensional theory. And this isn't a typo. The cubed is correct. If you think about how the dimensions work, now you've got a 5th dimension in your theory. That is added on to a part which should look familiar. So this looks like the four-dimensional Einstein-Hilbert action. So this is the action for the sort of brain part of the theory, where now instead of the Planck's constant, we've sort of generalized it to some sort of four-dimensional mass scale. And then there is the matter part of the action as well. I've written it in a slightly different form. Sorry about that, but this is just the standard matter part. So we've got our five-dimensional metric G tilde, and then there's a sort of induced metric on the brain, which is four-dimensional, which is related to the five-dimensional metric by this expression. So contracting with derivatives of the five-dimensional coordinates. And what's going to be really important about this theory is a particular scale, which we can interpret as a distance scale, defined by the ratio of the four and five-dimensional masses that appear in the respective parts of this action. So we will call this the crossover scale. I should say I've set factors of c to 1 in most places in my slides. So this is the distance scale if you put the factors of c in. Okay, and we'll see why that matters shortly. But you can think of this crossover scale as kind of the physical distance you have to go to on the four-dimensional brain before you become sensitive to the five-dimensional space-time. So below the crossover scale, universe kind of looks normal, 4D. Above the crossover scale, it could be really big. It could be five-dimensional. Okay. So we're going to do a little bit of mathematics to get to some important equations in this theory. So we need to put in a line element. This is usually how we think about writing down, for example, the FRW metric of standard cosmology. So here's my equivalent of that FRW metric, but it's a little bit exotic looking. So we've got, as usual, time coordinates squared, spatial coordinates squared, but now I've got the sort of fifth dimension sitting in here, which I'll label as y. And so normally you'd have a scale factor a just depending on the time, tau, but now it depends on this coordinate y as well, which is a bit unusual. This object gamma here is just the usual contraction of the spatial metric on the three-dimensional slice. So if we're doing a universe without curvature, keep life simple for now, it would just be the identity matrix. And I've had to be a bit more general than I would do in normal FRW, where I might go to conformal time and this object n would just be the same as the scale factor. I'm going to keep it as this more general function, which gets called the lapse function. Okay, so we can vary this action for DGP. We can get the field equations for DGP just as we did before, and we can plug in this kind of exotic looking FRW-like line element. And that will get us to something that looks like the five-dimensional equivalent of the Einstein field equations. Okay, so this should all look completely familiar. It's just that we've got tildes on everything to show it's 5D, and we've got our 5D constant sitting in there. Sorry, 5D constant, that's confusing. The constant itself is not five-dimensional, it's the mass scale associated to those extra dimensions. Now this object sitting on the right-hand side, the five-dimensional stress energy tensor, contains two contributions. The first contribution is just from normal matter, right? Baryons, radiations, etc. And we said normal matter lives on the brain. So considering some matter source without anisotropic stress, it would just have the normal diagonal form, and that kind of fifth dimension component would just be 0. Then this extra contribution to the stress energy tensor here, which I've called U. It is a big complicated mess of derivatives of the scale factor A and this lapse object N. I'm not going to write it out explicitly because it would just take up a lot of time and mess. It is written out in my lecture notes that I linked to, and much of that derivation came from this very nice book by Amendala and Tsujikawa. Okay. So the next steps of the process that I'm not going to do, but I'm going to describe them verbally, what you would do to continue working with this theory, is you would write out all of the components of these field equations, and notice that there'd be some kind of new components that you wouldn't normally be there that depend on the fifth dimension. And you demand continuity of your space-time metric across the brane. And that gives you some continuity restrictions on the scale factor and on that lapse object n. Okay, and we put the brane at y equals 0. And you can use those continuity equations, you substitute them back into your modified field equations, and you do an integral, and then you combine your field equations. So there's a lot of just messing around, basically solving and combining equations to kind of try and reduce the number of variables. So if you go through that process, you can arrive at what looks like a modified version of the good old Friedmann equation for cosmology. So the Friedmann equation on the four-dimensional brane for a universe without curvature is going to look like this. So h squared, that should look familiar, okay, where this Hubble factor is kind of almost defined as normal. It's just the derivative of the scale factor. Equal to, on the right-hand side, we've got regular matter. I've just written out cold dark matter here with the four-dimensional Planck's constant. But there's this extra term here. Now, if this object h divided by rc, remember rc was this kind of crossover scale, if that's really small, so if the crossover scale is really, really large, this term is kind of negligible, and you've basically got the normal Friedmann equation from lambda CDM. Okay. However, we can also consider what happens at late times in the universe. So late times in the universe, cold dark matter has kind of red-shifted away, right? Its energy density drops. And so this dark matter sector effectively goes to 0 on the right-hand side. Okay, so radiation, cold dark matter, neutrinos, they've all red-shifted away. So this right-hand side becomes 0. And then I've just factorized the left-hand side. And this equation has two solutions. H equals 0 is not an interesting solution. That's not a universe that's expanding or contracting. So the only remaining solution is that H tends to 1 over the crossover scale. And, sorry, I should have said there's this constant epsilon here, which can be plus or minus. That's just accounting for two solution branches in the theory. We're going to take the branch for now where epsilon is 1. So H tends to this positive value, 1 over the crossover scale. And what's cool about that is the same behavior that we get to at late times in lambda CDM, right? When dark energy, cosmological constant, dominates the universe, the Hubble factor tends to a constant once all matter has redshifted away. So we've got a self-accelerating solution, something that acts like lambda CDM does. But we've got this value of that self-acceleration kind of has this physical meaning. It is telling you about the respective energy scales of our four-dimensional brane and five-dimensional bulk space-time. So when it was first introduced, DGP gravity made a lot of excitement for this reason. It was a kind of genuine self-accelerating cosmology where you didn't have to put in that cosmological constant by hand. Now, that seems super exciting and positive. There is going to be a little bit of an update to this story tomorrow, where, hopefully, if I get time, where sadly things didn't work out so well for DGP in the end. And so in the end, it turned out not to be a viable theory of gravity, at least in the way I've presented it today. But maybe we'll come back to that story for tomorrow. Okay, so we've been jumping around this modified gravity model space. So first of all, we met scalar tensor theory and Brans-Dicke theory. Then we met F of R gravity. And then we met DGP gravity, a higher dimensional theory. I'm going to introduce you to one more action, only one more modified gravity action. And in some sense, this is going to be the most important one for what we're going to talk about tomorrow when we really look at linking things to the data. To introduce this fourth and final action, first of all, I'm briefly going to go back to scalar tensor gravity, which we had earlier on. And this was our general form for scalar tensor gravity before I made a field redefinition. And I'm going to bring in just a little bit of notation to help us out going forwards. So I'm going to introduce a variable called x, which is just up to constants, a factor of -0.5, nablify. So x is kind of representing the canonical kinetic term of a scalar field. When we had quintessence, it just had this canonical kinetic term. So this kind of object here is effectively x up to a factor of -2. Okay, and this might seem like a bit of unnecessary notation. The reason I bring it in is that in some modified gravity theories, that canonical kinetic term, x, can be replaced by a more exotic kinetic term, which will be some function of x. Okay, that's what I'm trying to represent here. So there's a class of theories called k-essence, in which the kinetic term, as I've indicated, is some functional form, x plus x squared, etc. Okay, so that's just a little bit of notational wrangling. What we're trying to move towards is answering this question. What is the most general version of a scalar tensor theory? That is a theory containing a metric of space-time, like GR does, plus one extra scalar degree of freedom. What is the most general version of that theory we can write down? Because if we can do that, if we can write down something that we know is like the most general version of that theory, we can just work with that one model. And then everything we've spoken about today, like Jordan-Brans-Dicke, quintessence, k-essence, they'd all just be kind of subclasses of that gravity theory. It's like trying to write down the parent theory that has kind of offspring. So let's try and do that. Again, I'm not going to take you through the derivations. This has been done. And actually, this kind of Uber theory, this parent theory, was written down kind of by accident in the 1970s by a chap called Gregor Horndeski. And so it has the name Horndeski gravity. Okay. And this is the most general action for a metric and one scalar field. And that's kind of proved mathematically in Horndeski's original papers. Now, it is quite a beast to write down. So we're going to write it down as a series of terms, right? We're back in 4 dimensions, normal volume element. There's going to be a series of terms here. And then we've just got matter as usual. So here come the terms, right? Here we go. This is kind of as big as the expressions get. So there is this stack of terms that contain a scalar field and the metric. Let's talk through them one by one. The first term, L2, is a function we call k of the scalar field and its kinetic term x, which I wrote in the corner there as a reminder. Right, and we needed this because we said you could have these generalizations, these exotic kinetic terms. So that's the sort of the generalization of a kinetic term sitting in our action. Then the next term, L3, contains another function of phi and x, we call it G3, multiplying box phi. Now that kind of seems random. Why box phi? Well, first of all, it is a term you can write down that preserves all the symmetries of the action. It preserves the second order nature of the field equations. So it's sort of allowed to be there. That is the particle physics perspective. If it's allowed to be there by the symmetries, we must write it down. And actually, again, we'll see tomorrow that this term in box phi is really important for something we call Weinstein screening. We'll come back to that. L4 stuff starts to get a little bit more complicated. So it's got this, again, function of phi and x we call G4 multiplying the Ricci scalar. So this is where GR hangs out. Okay, GR is living as a subcase of this Horndeski action where we set this function G4 just equal to the Planck mass squared over 2. And we set all these other functions, k, g3, and g5, which we'll get to in a moment, equal to 0. That's how we get GR out of this general framework. And notice if g4 is a constant, then this term here, which contains a derivative of g4 with respect to x, would vanish. Okay. And finally, the biggest part of the Lagrangian, L5, contains another function of phi and x we call g5. And I think this is the hardest one to interpret. Basically, it contains all these weird derivative couplings of the scalar field. The kind of property this big term has in square brackets, it looks like it should be higher order, right? Because there's 1, 2, 3, 4, 5, 6 derivatives of the scalar field sitting in this term. So it looks like it should produce field equations that have more than second order time derivatives. But actually the particular structure of all these terms here means those higher order terms get cancelled out. And so despite appearances, this term will only produce things that are second order in time derivatives. So this is a big beast, but as we said, this is the most general thing you can write down. And just as another example to sort of help orient ourselves, Jordan-Brans-Dickey theory, JBD theory, we mentioned earlier, that would be obtained in the limit where this function G4 is set to be the scalar field phi. And the term k here is just made proportional to x over phi, and G5 is 0. Sorry, I should have written that down here. And G3 is 0 as well. So basically, there are these 4 functional objects, K, G3, G4, and G5, and by plugging into them different expressions, you can cook up all sorts of different kinds of theories of gravity with one extra scalar field. And here is a table just showing an example of this, right? So on the left-hand side here, first column, we've just got the names of lots of different modified gravity theories. Some of them I've mentioned already today, some of them like the Galileons I haven't mentioned yet. And here is how they map on to particular choices for those 4 objects, K, G3, G4, and G5. So this might seem like a bit of an unnecessary abstraction. But the reason this is really powerful, we will meet tomorrow when we want to compare our theories to data. We don't want to have to do those computations and those data analysis in all of these models individually. And of course, there are many, many more models of gravity than I've shown here. So what we want to do is just constrain this framework of Horndeski. And then if you care about some particular theory of gravity, you can come along, use these mappings and work out what the constraints are on K essence, for example. Okay, so we will come back to Horndeski gravity. I have one kind of final side note before we move away from the modified gravity Lagrangians and start doing more phenomenology, which is a side note on extra fields. So today I've been talking about scalar field, scalar field, scalar field, and Horndeski as the kind of uber theory of scalar fields. And the reason we do that, everyone loves scalar fields, right? They're easy to work with, but we can build modified gravity theories that have other field content, right? And remember that was a way of avoiding Lovelock's theorem, was to couple in other fields. So you can consider adding a vector field to the metric of space-time. One of the slightly weird and tricky things about vector fields is, of course, they pick out directions, right? That's what vectors do. And you definitely don't want to break the cosmological principle of homogeneity and isotropy. You don't want to pick out a particular spatial direction in the universe. So when you bring in a vector field to cosmology at the background level, that is the sort of FRW smooth, maximally symmetric metric level, it has to point in the time-like direction because that's the only preferred direction in cosmology, right? There's no spatial direction preferred, but there is an arrow of time. And there is a kind of equivalent for Horndeski gravity for vector tensor theory. So the kind of general version you can write down. It's called generalized Proctor theory. I give some references for it here. This is not the Heisenberg of quantum field theory. This is Lavinia Heisenberg, who worked a lot on these theories. You can also bring in other tensor fields. So you can have what we call a bimetric theory, two tensor fields. This stuff gets very messy very quickly because you've kind of got two copies of everything and there's loads of tensor indices flying around. But this is a good review of things to start you off. And finally, you can throw in the kitchen sink. That is, if you're really a bit of a masochist, you can have tensor, vector, scalar gravity. So that's one of everything, a metric, a vector, and a scalar field. And again, there's a whole bunch of references on that, but SCORDIS is a good place to start. Okay, breathing point. That is the end of the modified gravity Lagrangians. What we are going to do now is to start doing some cosmology. So we'll start putting some of this into practice, and then we'll kind of pick up that story again tomorrow. So let me just have a brief breather. Okay. So to put this into practice, here is my mental map. At least this is how I think of things. Kind of sitting at the top, you have that modified gravity Lagrangian, whatever theory you're working with, the things we've just been writing down. And as we've said already, if you vary that Lagrangian with respect to the fields, so with respect to the metric and say the scalar field, you get out your equations of motion for your gravitational field, but also you get extra equations of motion for, say, your scalar field. Now, as we did already in the case of DGP, we want to really study the cosmological solutions here. So we plug into those general field equations an FRW metric or something like an FRW metric. I like to work in conformal time, so often I will plug in this metric here. And that gets you to what I call the background equations. So it's the homogeneous cosmology. So that's things like your Friedmann equation. And if you've got a scalar field, your equation of motion that just tells you about the time evolution of the kind of homogeneous part of that scalar field. And you can solve those, and we'll do an example of that in a moment. But then to make progress, you have to move beyond background cosmology, right? The universe is actually full of structure. And so your first place to start will be linear perturbation theory. So again, ironically, I can reuse the same expressions I had for variations of the action. You need to perturb your metric and perturb your scalar fields. Okay, and what that does is it sort of leads you into two sectors. So this metric perturbation will have a spin 0, technically a spin 1 part, although we don't need to worry about that, and a spin 2 part. And the spin 2 part of your perturbation, of course, will give you gravitational waves. And we'll come to that sector tomorrow. The spin 0 part, so the kind of scalar perturbations of your metric, are what lead you into cosmological perturbation theory. So that's studying the behavior of small density fluctuations and small potentials in your universe. We'll do a bit of that in a moment. However, of course, you're probably aware there are definitely regions of our universe, particularly on small scales, where linear perturbation theory does not hold. So that's usually taken to be when your dark matter density contrast, which I've defined here, so it's just the fluctuation above the mean matter density. When that gets close to 1, or certainly when it gets larger than 1, you can't do linear perturbation theory anymore, and you are in the non-linear regime of structure. And this is when you have to get out the big guns. So you have to do things like run n-body simulations of how dark matter particles actually collapse under gravity. And I'm just showing a snapshot of something there. So this is the kind of map that I think of how you kind of move through your theory towards observables. I will say, of course, there are other observables not on here. So I went to cosmological solutions, but of course, once you've got your field equations, you could put them on a black hole space-time. And there's a whole, industry in studying black hole solutions and behavior in strong field regimes. What I'm going to do is just take you through a little bit of an example then of some of these background equations, and we'll do a little bit of linear perturbation theory that will set us up for connecting to observables tomorrow. So let's take a worked example. Here is a gravity theory I haven't shown you yet, but it's a member of the Horndeski family. So it's a scalar theory with a scalar field. It's called cubic Galilean gravity. And technically, it's a dark energy model, not a modified gravity model, because you can see here, this part just looks like the action we had for general relativity. So we haven't actually changed the laws of gravity, but we've got some funky scalar field in here. It's got a standard canonical kinetic term with some parameter C2. And it's got some weird new term that involves box phi. We saw that in the Horndeski Lagrangian. Okay, and these new terms have got coefficients C2 and C3. So we crank the handle, right? Our procedure, we vary with this with respect to the metric and the scalar field. We plug in an FRW metric, and I'm just going to take the matter sector as only having cold dark matter. I won't worry about radiation today. And you get components of your Einstein field equations. So again, stuff starts looking pretty messy pretty quickly. You also get your scalar field equation of motion at the background homogeneous level. So it doesn't contain spatial derivatives of the scalar, but it does contain time derivatives. And these all look pretty ghastly. But what I want to do is sort of help you find the sort of familiar limit here. So I've underlined in green the pieces that should be familiar. Right, so sorry for keep changing the constants here, but kappa is just 8 pi g, so just the standard constants. And this part here would then be the standard Friedmann equation, but it's got these new scalar field terms in it underlined in red. And again, this would be what I call the Raychoudhury equation, the kind of second part of the Friedmann equations. Again, as normal, but now with some extra scalar field kind of acting like a source of pressure. And then, of course, the scalar field equation of motion is completely new. That wouldn't be there at all in standard lambda CDM. So whilst this looks kind of ugly, at the end of the day, it's a set of coupled second order differential equations for the scale factor and for your scalar field phi. And so you can write a little Python code and you can solve these coupled equations. So here is a plot showing that solution for this particular theory. And what's being plotted here is the Hubble factor as a function of scale factor divided by the equivalent lambda CDM Hubble factor. So the dashed line at 1 would just be kind of standard cosmology. And the blue line here is cubic Galilean gravity. You can see what it's doing is it's actually increasing the Hubble value at early times by about, what's that, 2 to 3% or something. And then at late times, there's this kind of weird dip where suddenly the Hubble factor drops below its normal lambda CDM behavior and then comes back up. And it so happened the paper that I took this from by Barrera et al., it actually had on it as well a solution for DGP gravity, which we saw earlier. So that's kind of cool. So there's a green dashed line here, which is showing a version of DGP gravity. It's actually a little bit different to the one I showed earlier. So you can see different modified gravity models do different things. But to be a good modified gravity model, you can't completely go crazy and go a long way from lambda CDM. You've kind of got to stay within a few % of the lambda CDM expansion history. Otherwise, probably you would have been ruled out by observations already. So that's just a worked example of this sort of step in green, right? Solving the background equations. And what we're going to do in our remaining time today is to delve a little bit into this cosmological linear perturbation theory sort of step. So to do perturbation theory, we need to perturb our line element. We need to introduce a mathematical description of small fluctuations about our FRW universe. And so I've written down on the slide here a really common piece of notation. We've got our usual scale factor, but there's now these two small perturbations to the diagonal parts of our metric, which we call phi and psi. And some of you will know this is like a particular gauge choice, which is conformal Newtonian gauge. So you plug this metric into your field equations. We're just going to do this in GR for now, just to get the standard case on the screen. And then as well as your background cosmology, you've got perturbed field equations, the kind of delta version of your field equations. And you look at those equations, they involve matter density perturbations, which I've just defined again down here, and also these two metric potentials phi and psi. And with a little bit of manipulation, and this is done in those lecture notes that I linked to, there's three equations that you can arrive at, which are really these sort of important ones for us. The first one is the Poisson equation, which tells you about how the spatial derivatives of one of these potentials, psi, are sourced by matter density perturbations in your universe. Right, and implicitly here there's a sum over dark matter, radiation, baryons, all the usual species. Then you can also get to a second relation which looks very similar. I'll call it the Weyl potential because that's the name given to the sum of these two objects, phi and psi. And this is what appears when you do lensing calculations. So when we do a bit of lensing tomorrow, I hope we'll get time for some lensing, you care about this particular object. And again, it's related to your matter density perturbations. And the key thing is that in general relativity, you can derive identically at late times, these two potentials phi and psi are actually the same. Okay, but that's a very special relation, and that's going to change very often when we go to a modified gravity theory. So you get these three equations from your Einstein field equations. Just for completeness, I need to write down that there are also two more equations that come from perturbing the conservation of your matter stress energy. So they're written down here again, they're derived in the lecture notes. So delta is just the matter density perturbation, theta is a velocity perturbation of your fluid species. And so you get these two more equations that link changes in densities and velocities to the behavior of these metric potentials. Now, this is the situation in GR. How does this change when we go to modified gravity? So I'm going to change the equations in the middle here. Here we go. So I've done this schematically. Notice the equations down the bottom haven't changed. Some theories of modified gravity can change them with weird couplings, but I'm going to leave them unchanged for now. So I'm doing minimally coupled modified gravity. But in my Poisson equation and my Weyl potential, I've picked up these two factors, I'll call them mu and sigma respectively, which, if you like, are placeholders for modified gravity stuff. If you work in a particular theory of gravity, you can work out what this stuff is. But there's generically some function of time, which I've represented with the scale factor A. And also it can be a function of scale. So I've put in a Fourier wave number K. And that appears in the Poisson equation and another factor in the Weyl potential relation. So you change these relations in some way. Another really important property is that these two metric potentials, as I've said already, are generically no longer equal to one another. So we're just going to do one more thing before I stop for a few questions, which is I just want to get you to the point to sort of see how this impacts the growth of structure in your universe. Okay, so one sort of further step of manipulations. We're going to take those two equations that describe the density and velocity perturbations of our matter sector. And it's pretty straightforward to combine these two into one equation. You just take a derivative of the one on the left, you substitute in the equation on the right, and you use the Poisson equation to replace this nabla psi squared by the expression we had previously. So now we've got a second order differential equation for our dark matter density fluctuation delta. But notice that factor mu has appeared. So the change in the Poisson equation has propagated through to this relation. And I've been a bit sneaky and I've dropped the scale dependence of mu for now because it's a lot weaker than the time dependence. So I'll just keep the time dependence. You can solve this equation. Indeed, you might have solved this equation already in one of your undergraduate courses in the case of a matter-dominated era, if omega n is 1. And if you do it in GR, so mu is 1, you can solve it by hand, and you should obtain the solution that delta is proportional to the scale factor. Tells you that density perturbations grow in the matter-dominated era. There's also a decaying mode, which you don't care about. So what you do in your modified gravity situation is you've got to solve this equation again. Now it might be a bit more complicated because you've got this extra function of time in here. And whilst I'm writing this in a general form, of course, to solve it, you'd have to go to some particular theory of gravity and plug in what is this object mu. So when mu is different from 1, the solutions will be different. That means dark matter density fluctuations will grow at a different rate than in lambda CDM. And again, I thought I'd stick with the same examples, so borrowing from the same paper. Here is a sort of solution of that equation in Galilean gravity and in a version of DGP gravity again. So what you're seeing here is actually delta divided by its lambda CDM value minus 1, well, squared and minus 1. The flat line here would be the lambda CDM solution. You can see the cubic Galilean. It looks like GR for a long time, but it's actually making density perturbations grow faster than they would in lambda CDM at late times in the universe. And DGP gravity is doing the opposite. It's suppressing the growth of perturbations. And there are 2 other dashed lines on here. Don't worry about those for now. They're not important. Okay, we will come back to this story of kind of how density perturbations grow and how we can constrain those things and use them to test gravity tomorrow. So the plan for tomorrow was to, we'll sort of change gears a bit to start with, and we'll talk about gravitational waves in modified gravity. And then we'll kind of revisit that Horndeski framework to set ourselves up for this very general connection to data. And then we'll do that. We'll tell you a bit about how large-scale structure actually constrains these very general theories of gravity. And I think I will leave it there for today and happily take any questions. I can't see Slack right now, but I could take questions in the room if there are any, and I could certainly respond to Slack questions later on.
Thank you, Tessa. Thank you. Thank you. We can take a couple of questions maybe now, and then we'll have a break. Let's just be brief on the questions. We can also send just like 1 or 2 questions. Vicente, right?
Hi, Tessa, for the very nice lecture. I wanted to ask you, I think on slide 29, you showed like a table with how can we choose the free functions of Horndeski for a specific model, and you included DGP, but that was in 5 dimensions. And I wanted to ask, is it a different DGP model?
Very good. Very good. So the important thing here is it says DGP subhorizon. So actually what happens is in this subhorizon limit where you are below the crossover scale that we talked about, DGP starts to look like, guess what, a scalar tensor theory. Everything seems to come back to scalar tensor theories at the end of the day. And so in that limit, DGP can be mapped onto Horndeski gravity, but it won't capture the full 5-dimensional properties of the theory on the largest scales.
Thank you so much.
Thank you. Yeah, 1 more question, and then we'll break. 1 more question.
Hi, Tessa. Thank you for the great talk. So in the scalar tensor gravity actions that you've showed us, you mentioned that the kinetic term kind of gets modified a bit. But looking at that form, to me, it also looks like kind of a derivative coupling kind of term. I was wondering if you had any thoughts on that.
It gets modified, so it can be replaced by other general forms, as is going on in k-essence here. You say it looks like a derivative coupling. So I guess you're saying, well, let me clarify. You're saying nablify is kind of not too different from the sorts of things that are appearing here in the Horndeski case. Is that right?
I guess I was specifically talking about phi times like derivatives of phi. You know, if there are like 3 of them, that kind of to me looks like an interaction term more than a kinetic term.
Right. Yes. So when you say 3 derivatives of phi, where do you have a slide number that you're referring to?
Oh, I don't have the number, but it was in the first half of the talk, and it was when you were talking about quintessence, and then you had phi tilde, and I think it was right after that point.
Oh, let's go back.
Yeah, I guess right here is probably fine. We have the kinetic term for the scalar field, but that doesn't just have the derivatives of phi. It has some other phi's kind of multiplying that. And from field theory, that to me just looks like an interaction term more than just a kinetic term.
Okay, fair enough. I mean, in some senses, it's a little bit of a matter of labeling. I call this kinetic term because when I go to Horndeski gravity, got to pan through my lectures now. That kind of term will fit into here, k of phi and x. But you're right that it's not just a function k of x that I said was the generalization of the kinetic term. So I completely get that it could be interpreted as a derivative self-interaction. I think this is really just a matter of labeling of these buckets, but it's not going to be too important at the end of the day.
Okay, awesome. Thank you.
Thank you very much, Tessa. Thank you. Let's take a half an hour break. We'll start 10 minutes after. Let's have our photo taken first. Thank you, Tessa. We'll see you again tomorrow.
See you tomorrow.